So generally this electrophile will be unstable. This plus charge will be either on carbon or nitrogen. That is going to be very unstable. So this electrophile will not move out. Like this electrophile will not act as a leaving group here. The one which is stable, that moves out and exists independently. If H plus is more stable than E plus, H plus will move out. And in the most of the case, in 99% case, H plus will move out. So what we will do is, if we remove H plus from here, if H plus goes off, it will lose electron, and that electron will go into the orbital of this carbon. This carbon is going to have negative charge, and this negative and this positive is going to form a pi bond. So I'm straight away drawing the pi bond. Hope you will not have any problem. There's a pi bond generated on this position because of removal of this hydrogen. So if you remove hydrogen, there's a pi bond generated on this in this position, and the rest of the 2 pi bond will draw as it is. Plus the electrophile will be remaining intact. So the problem is solved, and we are happy again. The aromaticity has been regenerated. That was the concern, and we are happy that aromaticity has been regenerated. And since aromaticity has been regenerated, this reaction is a possible reaction. So what has happened is, we put an electrophile in the system in benzene. We had a hydrogen on this position. Now this hydrogen has been substituted by this electrophile. So this is a substitution reaction. The reaction is taking place, the reagent or the reactive species here is electrophile. So this is electrophilic substitution on benzene ring. This is the idea. Now in all the reaction that we are going to see from now, in general we'll have a electrophile. Now that electrophile will be different in different kind of reaction, but the mechanism will be the same, exactly the same in all kind of electrophilic substitution reaction. So let me recapitulate you what has happened, and then this will be the last or the second last time I'll show you the mechanism. Rest of the time we will directly see the reaction without bothering about the mechanism, because mechanism will be the same in all kind of electrophilic substitution reaction, whether it is alkylation, acylation, nitration, sulfonation, whatever it is, the mechanism will remain the same. We have a benzene ring, we have a electrophile. Electrophile approaches the benzene ring. Because of the field effect of electrophile, a charge polarity starts to develop on the carbon, and the opposite charge develops on adjacent carbon. That is quite natural, because of the electronic density are moving towards this carbon. Obviously they are moving away from this carbon. So this carbon will start to become electron deficient if this carbon starts to become electron rich. Now that process continues, and sufficient amount of electron deposits or accumulates in the orbital of this carbon. Now when the electrophile approaches sufficiently close, then the electronic transition starts. Electronic transition starts from the orbital of carbon to the empty orbital of electrophile. Now during that transmission, a bond is formed between the carbon and electrophile. This is how electrophile approaches and get attached to benzene. Because benzene is electron rich, it can offer its electron to the electrophile. Now when this bond has been completely formed, there will be a complete plus charge on this carbon. Now this plus charge will be stabilized. This will be the RDS of the reaction. The RDS is the slowest step, and the slowest step is the most difficult step, and the most difficult step here will be breaking the aromaticity of this benzene ring. Now in RDS will be not very difficult to be crossed, because the plus charge created in the RDS is quite stable because of sigma complex. Because in sigma complex we have conjugation of this plus charge with the pi bond, resulting in 3 resonating structures. Now those 3 resonating structures will stabilize the sigma complex. This will be same in all kind of electrophilic substitution. This E can be NO2 plus, this E can be R plus, this E can be a selenium ion, whatever. Now after sigma complex has been formed, now again aromaticity has to be regenerated. And aromaticity can be regenerated by the removal of any one of the group from the carbon adjacent to this plus charge. That one of the group is hydrogen, the other is electrophile. Most of the time H plus will be more stable than E plus, so H plus will move out and E plus will be remained intact. That's how electrophile will come in and hydrogen will move out. So it will be electrophilic substitution reaction. Now this is the general idea, this is the general mechanism of any kind of electrophilic substitution reaction. And now let's see some electrophilic substitution reactions in particular. And the first kind of electrophilic substitution reaction that you will find in your book is Federal-Kraft alkylation on benzene ring. In this reaction, what happens, we have a benzene, and in that benzene we add alkylinium ion R+. This R+ can be any alkyl carbocation, methyl, ethyl, propyl, isobutyl, pentyl, neopentyl, whatever. Now this is another thing, how this R+ has been generated. This will be seen in a moment, but somehow this R+ has been generated, and this R+ will get attached to the benzene ring, substituting hydrogen from the benzene, and S+ will be removed off and R will get attached to benzene. So this is how alkyl group will get attached to benzene ring, removing H+ from the benzene. Mechanism will be exactly same without the change of a iota of the previous mechanism what we have seen. Now this R+ is merely same as E+, that we are not going to see anymore. The mechanism is exactly same. What we are going to see now is how this R+ has been generated in the system. Because R+ is not a stable thing. I cannot store R+ in the lab and put or use whenever it is required. R+ somehow has to be generated in the system itself during the time of reaction. So what we do is we take alkyl halide or alkyl chloride, bromide, iodide, whatever. This alkyl halide we add along with a good Lewis base, and one of the common good Lewis base is aluminum trichloride or aluminum chloride. When you put aluminum chloride with alkyl chloride, R+, this alkylinium ion is generated, and AlCl4-, chlorine get attached to AlCl3, forming a salt with it, forming a complex with AlCl3, that is AlCl4-. Now how this happens, we have talked a little about this during resonance or during inductive effect, but I'll brief you once again very quickly what exactly is happening and how R+ is generated. Aluminium is having an empty orbital. The atomic number of aluminium is 13. Electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p1. Now this is up till here is neon. This is 3s2 and this is 3p1. Now aluminium has one unpaired electron. Aluminium in the ground state forms 3 bonds. For forming 3 bonds you require 3 unpaired electrons. Now it has 3 unpaired electrons when one of the electrons from 2s jumps into one of the orbital of 3p. So in 3s you are left with 1 electron. In 3p you have 1 more electron, but still one of the 3p is empty. This 3p is empty, and this 3p I have shown with the shape of a p orbital here. So one of the p orbital of aluminium is empty. That's why it's a Lewis base. Base is a species which accepts pair of electron. Now aluminium has a lot of electron. This chlorine atom has 3 pair of electron. This has lots of electronic density. Now whenever we will put these two together, always and always electronic wave tries to occupy as much of the space around it as possible, because it's a wave. It tries to expand and fulfill and cover whole of the space around it. So some of the electronic density, although I have shown it like dot, but you don't have to imagine it like particles kept like dots, like 6 of the balls has been kept here. The best way to imagine, to visualize this as smokes coming out of chimneys, like smokes is coming out and trying to expand, but somehow with the charge of the nucleus it is not expanding all over. Somehow it is confined to the region around the nucleus, but still it is free enough to penetrate out, to project out and move in any of the orbital around, right? So when you put AlCl3 very close to RCl, then these projections enters into the orbital of aluminium, resulting in the formation of a bond between chlorine and aluminium. That will result in release some amount of energy. That energy released will be utilized to break this bond further. When you break this bond further, then slight positive charge will be created on R and slight negative charge will be created on chlorine. So this chlorine will become further electron rich. Now it will further provide some electron to aluminum. Now there will be further formation of some bond. Now there will be further release, further amount of energy will be released. Now that energy that which is further released will be further utilized to further break this bond. When this bond is further broken, there will be further accumulation of charge on R and Cl. So this charge is going to increase, and this charge is going to increase as well. So this charge which has been increased on chlorine, that will result in more and more electronic wave going into the aluminum, strengthening the bond between chlorine and aluminum. The energy released will be utilized to break the bond between R and Cl, and this process will continue indefinitely until the whole of the bond between RCl has been broken and a complete one bond has been formed between chlorine and aluminum. So at the end of the process, what's going to happen is this R is going to be formed as R plus, and this Cl, taking both the electron of this bond, is going to move out as Cl minus, forming bond with aluminum. So this will result forming AlCl4 minus. This is how R plus is created. In books you don't find the explanation, so I hope I made you understand this. Nevertheless, R plus has been created if you add AlCl3 in RCl. This is very important, and this is something you must remember finally. Alright, so this is how R plus is created. So if I want to carry out alkylation, what I have to do is I have to take benzene ring, I have to add any RCl, any R, whatever R I want on the benzene ring as an alkylated product, and a corresponding Lewis base. So what I have to do is I have to add RCl and AlCl3 generally we take. So that will create R plus, and R plus will carry out electrophilic substitution reaction based on the mechanism which we have already seen, right? So this R will come here, this H plus will move out, and this H plus and this Cl minus, which has been removed from this R. Actually H plus will be removed out from here, and this Cl minus has formed a complex, with AlCl3, that is AlCl4 minus. These two again forms HCl, and AlCl3 is regenerated to further react with rest of the RCl and benzene. This AlCl3 is a catalyst, it will be regenerated at the end of the reaction. The product would be alkylated benzene or alkyl benzene and HCl. That will be the product of alkylation. So suppose I want to prepare cumene. If I want to prepare cumene, and cumene, if you don't know, although I have told you before, but you might have forgotten, cumene is isopropyl. This is isopropyl benzene. Isopropyl benzene is cumene. Now if I have to prepare cumene by Federal-Kraft alkylation reaction, then you have to tell me what should be the R in my RCl. I take a benzene ring and I want to form a cumene out of benzene. So this R, look at this, look at the position of the bond. The bond, it will be bonded from the position where the plus charge has been created. Now the bonding of benzene is with second carbon, that means the electron deficiency must be on second carbon, that means plus charge must be on second carbon, that means chlorine must be on the second carbon, because from wherever chlorine is going to move out, that carbon is going to acquire a plus charge. So prima facie, although there are multiple answers, but prima facie, based upon the study we have done up till now, if you take this 2-chloropropane, and if I take AlCl3, then this AlCl3 is going to snatch out chlorine out of the substrate, forming a plus charge on the second carbon, and that second carbon is going to get attached on the benzene ring, forming cumene. Alright, this is how we're going to start understanding this electrophilic substitution. So this is alkylation. Now whatever R you take, depending on that, you will get a alkylated benzene. Not much to talk about alkylation, that's all. Now the second reaction in the list is Federal-Kraft. Now Federal-Kraft, I mean, he was a scientist, so the reactions are named after him. Federal-Kraft acylation. The second reaction is acylation. This group is acyl group. When this group get attached to benzene, that is called acylation. That's it. Alright, I take a benzene ring and I want acyl group to be attached on benzene. This reaction will be acylation. Now see, benzene ring is bonded with this carbon, the carbon on C double bond O. So before reaction starts, there must be a plus charge on the carbon of this C double bond O. Then only electronic transition will start from this carbon to the empty orbital of this carbon, and there will be a bond formation. So the connectivity is with carbonyl group, C double bond O group. So there must be a plus charge on the carbon of carbonyl group. That means I must have a selenium ion that will form acylation, that will produce acylation react product, or that will form a acylated benzene. Alright, now the whole understanding would be of as how this acylinium ion will be created. The mechanism will remain exactly the same, the mechanism which we have already seen. This electrophile or acylinium ion will approach benzene, sigma complex will be formed, and then hydrogen will be removed off, aromaticity will be regenerated. That is going to remain same in all kind of electrophilic substitution we are going to see. So we are not going to see the mechanism again, we are going to see how we will be creating this electrophile. So somehow if I create this acylinium ion, then acylation reaction will occur. This we understand. Alright. So acylinium ion, like based upon the understanding of the alkylation, how alkyl carbocation was created, we can extend that idea to create acyl ion or acylinium ion as well. So what we must do is we must take acyl chloride. This is acyl chloride, chlorine attached to acyl group. If I add AlCl3, again the same thing will occur as it did happen in case of RCl and AlCl3. Aluminum has an empty orbital, as we have seen a moment back. Chlorine has 3 pair of electron. This electron we never have to visualize in terms of dots. They are not particles, they are waves. So there are some electronic wave here in chlorine. Alright, that electronic wave is going to move out and enter the empty orbital of aluminum. Now the electronic wave that was previously on chlorine was attracted only by the nucleus of chlorine. When it is going to move into the orbital of aluminum, it is going to be attracted by the nucleus of chlorine and aluminum both. So the attraction power of that aluminum, the attractive force on that aluminum will be on that electronic density will be increasing, and that will be resulting in release of certain amount of energy. Whenever we have an attractive force energy is released, system is stabilized always. Like if you drop a ball, if you take a ball in your hand, if you drop it, then the force, attractive force of earth will operate, ball will come down, energy will be released, that energy will go to kinetic energy, and ball will ultimately fall on the ground and become stable. Now here energy is released in form of heat energy. So here when attractive force will operate, then heat energy will be released, and heat energy is released and bond will be formed between chlorine and aluminum. That heat energy will be further utilized to break this bond, and gradually this chlorine will shift away with this AlCl3, and this rest of the substrate will be left behind, and the electron of this bond will be gone with chlorine, because chlorine is smuggling electronic wave from this substrate into the empty orbital of aluminum. So what will happen is we will be having a selenium ion generated here, and this Cl minus will move out with aluminum chloride forming AlCl4 minus. This minus because this minus is coming from chlorine and this is neutral. So had this aluminum had positive charge, then it would have become neutral, but there's no charge on AlCl3 to neutralize the negative charge coming with chlorine. So this will exist as AlCl4 minus. So effectively Cl minus has moved off and forming or producing plus charge on this carbon. Now this is a selenium ion. A selenium ion. Now this is how a selenium ion is created. A selenium ion will be formed. A selenium ion will go to benzene ring, form sigma complex, substitute hydrogen from benzene, forming or having electrophilic substitution on benzene. And that's it. This is acylation. Now any exam is not going to ask straight away like this. What they do is they do a little bit of twist.